Welcome to Mrs. Mahoney's podcast 3.6. This is our last one of this unit. Okay, I can hear you cheering now, but it hopefully will be a quick one. We're still looking at electrons and we're talking about all this today, so that tomorrow we can actually go and excite some electrons in the lab when we do that flame test. So we're at the top of page 18, and let's just do some definitions and kind of look at what we expect to see tomorrow. So we're going to be still talking about electrons, but let's look at how electrons can act if they're not in that ground state, normal state. So we're going to be talking about electromagnetic radiation, or just light. And light is not just the visible light. That's one little portion of the EM. You're going to hear me say EM, electromagnetic spectrum, or this radiation. So it's just some form of energy, and it acts like a wave as it travels through space. What I think is most important is looking down here, look at the examples. Those are the types of examples that you need to know. You need to know, again, visible light, that's one example. X-rays, ultraviolet, UVs, infrareds, microwaves, radio waves are all types of electromagnetic radiation. I bet most of you have heard about all of those. Okay, so if we want to know what it is, and so it says label it, use this as a guideline. You don't have to put all the numbers. I'm not worried about all the numbers. What I want is to know how they are in comparison. So make sure that radio TV is down at this end. Then we have our microwaves. And so if we look at our length, these are really, really long. They're getting shorter. Then they're getting shorter. Okay, right here, look at how small our visible light is. Within this is where we have a visible light spectrum. Then we have UV from the sun. Then we have our X-rays that we need to have more protection. Then we have our gamma rays. When we start talking nuclear, we'll go back to the gamma rays. So take some time to kind of write this down. Okay, I'm also going to tell you, you need to know the colors of the rainbow. If you do not know now, Roy, G, Biv. Red, orange, yellow, green, blue. Okay, indigo is put in a lot of it. Indigo is kind of like a purpley. It's between the blue and the violet. And then violet. You need to know the order. I think most of you have heard that. So if you don't, put that down. If you want to get colored markers or something, you need to know that spectrum. Okay, we also have some lines from that. This is looking at the same thing, kind of putting it in perspective. Look at the difference in the wavelengths. So you have some blanks above it and below it. So at this end, our radio waves, really long wavelengths, clear to my gamma rays, which are really short wavelengths. Okay, look at down here, then it's opposite. If it has a long wavelength, it has a very low energy. My short wavelengths are a very high energy. So that's good, because radio waves, TV waves, they're all around us. Gamma rays, I don't want to be around those. They pack a lot of energy. Here's my visible light in the safe spectrum, but you know it's very close again to that UV, and we talk about the sun and how you need to not stay in the sun and skin cancers and everything. It's starting to get to that higher frequency, higher energy can do more damage. Okay, you have a question there. Why will yellow light cause the ejection of electrons from potassium, but red light will not? So that's saying if I shine some light, I can actually force an electron to kick off of it. This is how we get infrared sensors and doing different sensors. It's like, well, why will it happen? Look at the energy. Yellow's up here at a higher energy than red. So yellow has more energy, or you could say red does not have enough energy. So when I'm looking within the color spectrum, red is very low energy. Your violet is your high energy. You need to know that for your Roy G. Biv as far as the comparison, the relative strength of each of them. Okay, but wait, we're talking about electrons. What does this have to do with electrons? Actually, quite a bit. Comes back, we're finally going to spend some more talking about kind of Bohr. We're going to look specifically at a hydrogen. What can happen is called an emission spectrum. This word right here, emission, emitting. Know this word. So what happens? Okay, some vocab words. Ground state. That's the lowest energy state of an atom. Every single electron configuration we have been writing has been a ground state configuration. Okay, then what is an excited state would be if for some reason it's absorbed some energy and that electron then jumps up to a higher than normal place. So if I have an electron in helium that normally is in A1s2, some reason for helium, it goes up to an excited state could be if one of those electrons jumped up to the 4s orbital. Now that's not going to stay there very long, but it can do that. Okay, so when does that happens? It happens when some kind of energy is applied. But that energy, it can't stay up there. It's not going to stay up there. So what's going to happen then, it's going to fall back down to ground state. Well, that energy it took to put it up, it's going to release that energy, and sometimes it's being released as visible light. So they did some tests on this. Example, and I'm going to pick on somebody in class. I'm just trying to think of, it'd be easier definitely if you're all sitting in front of me. Front row, let's go for some of my J's. Josh. You can figure out which Josh I'm talking about. If I have a cattle prod, if you know what a cattle prod is, it's got a little bit of a poke on it, but it also has a charge to it and is used to make the cattle go where they need to go when they're trying to herd them. Well, if I took a cattle prod and for some reason surprised him and stuck him in the bum with the cattle prod, I bet he would jump up because I've supplied with some energy. He can't stay up there in a jumped state. He's going to come back down. And somehow I'm betting when he comes back down, I bet he's releasing quite a colorful language as it's coming back down because gosh darn it hurt. That's what electrons do. They may not do it verbally yelling, but when they fall back down, they release energy. That energy, if it falls in the spectrum of visible light, we can see it. And that's what we're going to be looking for tomorrow. So when they did this, they thought, remember this is how they were back in our history, they thought, okay, electrons could go everywhere in an atom. They could exist everywhere. So this is what they expected to see, a continuous spectrum. So in your box where it says continuous spectrum, you just need to know that it's every color, because we need to say what's the difference. Okay, but really what they saw was just a few lines of color, and that's called the line emission spectrum. So this was huge because it's going, wait a second, electrons may not be able to go exactly where they want to go. There must be some limit to that. They must be within some defined areas. So this is what the experiment looked like. They took a hydrogen tube. Like I said, we're going to do this on Friday. Instead of a prism, you'll be wearing some glasses. And then what they saw were only a few, right here, see these? They only saw 1, 2, 3, 4 lines of colors. So in fact, then they later on were able to name them. Well, excuse me, these were named for the people. They discovered some infrared and some UVs, but these were the ones that we could actually see. So that made them to say, okay, electrons cannot exist wherever they want within it. So this is how Bohr came up with his model. Looking at it, he said, okay, here's my little electron. This is a photon of energy. What's it going to do? It's going to excite an electron. So make it to look like this. This excited electron might jump all the way up to here. But just like the cattle prod, it can't stay there, so it falls back down. This is what we need to know. This is what we care about when it falls back down. And it falls back down, what does it do? Kicks out some energy. If it kicks it out in the visible spectrum lane, we will see different colors. So there's some blanks underneath there, and here's your lines for filling it in. Each line is produced by the emission of photons. It's just a little packet of energy, of certain energies. And this energy, it's just the difference between a ground state and excited state. So what they discovered then, looking at this, you can draw on some arrows. So these are my energy levels. My first energy, second energy, third, fourth, fifth, sixth. Okay, so this is saying if it's falling from a second down to the first, or at least this much energy. The longer the line, the greater the energy. That's why these are in my high energy spectrum, which is my UV. These are little bit lower. Now this is the one that was right there close to the UV. This is in my visible spectrum. These were in my my lower energies, or my infrareds. So they knew then it's just like a floor on an elevator. The electrons couldn't exist in between the floors. They could only exist at these certain energy levels. And that's what we've been using when we've been doing our electron configuration. And that's why we say it's at a first energy level, second energy level, third energy level. It's because of this research we know that they exist at those specific energy levels. Okay, so on the top of the page, next page, on 19, why did this happen? So here's some key points that you need to know why this happened. Those electrons moved in set orbits. This is, again, remember we're Bohr talking here. That was at set energy level. Only difference, we now know they're in orbitals, but it's still, this is the same, set energy levels. So what happens, that energy difference between them is fixed. It's the same. That's what I mean by fixed. It does not change. So if this is the same, then the difference between the energy levels is going to be the same in all of the different atoms. So therefore I'm only going to see some colors. This is unique in every single element. Every element has a unique spectrum. But look at every element. We've just been doing electron configurations. They all have a unique amount of electrons, so therefore they have a unique spectrum. We can actually use that to identify elements. And we're going to, like I said, we'll be looking at that on Friday some more and look at some of those spectrums. And you're going to be seeing it tomorrow in the flame test and using it to identify. Okay, this section does have some math with it, so we're going to look at the math now at the rest of page 19. And there's a couple different reasons of why the math, two different equations, and there's two different reasons we have two different equations. First thing, light acts like a wave. Here's some of the reasons, some of the properties. We have interference. You can have polar eyes. You think about polarized light sunglasses. It cuts out some of the wavelengths. Diffraction, refraction, light can bend around a corner. All of these are properties of waves. So since it's properties of waves, we can calculate it using the wave equation. If you look on your, what color is it? Sorry, salmon colored, I was going to call it purple, salmon, pink, whatever it's called, formula chart, you're going to see three equations together. And the first one is the wave equation. C equals frequency, okay, again we're borrowing from the Greek, that's lambda. That stands for C, that is your velocity. Well, for us, for all of us, we're using that's a constant, and it's going to be the speed of light. That's also on your reference sheet. So in case you ever sit there going, oh my gosh, I can't remember what the speed of light is, use your sheet. So 3 times 10 to the 8th meters per second, that is the speed of light. F is your frequency. Okay, frequency is how many times a wave hits you in a certain time interval. If you're standing at the beach and it hits every 2 seconds, or if you're standing closer and it hits you every 30 seconds, that's what it's talking about, is how often does it hit you. That lambda, it's a wave length from one crest to another, or from a trough to a trough. Okay, typically that's in meters, centimeters, or nanometers. Nanometers are going to be back. But look at this. To use your wave equation, make sure you pay attention right here. This is in meters. So if I give it to you in centimeters or nanometers, which I would never do, of course, yeah, right, this means you're going to have to do some converting. I don't know why that was there. Okay, so let's look at an example. Here's my problem we can work. What is the frequency of green light, which has this wavelength of 4.9 times 10 to the negative 7th meters? Yay, I was nice. There's meters. List out my formula. What do I know? Well, I know my lambda. I know my wavelength. What else do I know? Oh, yeah, frequency. It's the same. So now you're just going to plug it in and we can work it out. Okay, what I have done here is I just rearranged my equation up here already. I said, okay, I'm looking for frequency. I'm just going to divide both sides by lambda, by my wavelength, before I even start. So these cancel. So what I get, frequency is speed of light over my wavelength. And then I just plugged it in and solved it. And so you get that your frequency is 6.12 times 10 to the 14th hertz is your label, Hz. It stands for hertz, Hertz. If you don't like doing this, then you just plug in C is this, frequency is this, and then how do I divide? I divide by your wavelength. You have to do the same math. You can just either do it before you put the numbers in or after. So just three variables. We're plugging in, letting our calculator chug out the answer. Well, there were other part of the scientists who had this argument who said, okay, now light is like a particle. It's like little photons, little quantums of energy. And this is why. They had their own reasoning. They said light can have reflection. There is the photoelectric effect, which is just the emission of electrons from a metal. This is how we get radio controls, or you have your remote controls, and how you can turn your TV channels from across the room, the photoelectric effect. But this also depends on the frequency, low frequency, and I'm not going to get those electrons coming out. Well, we have a little quantum of energy, and it was Max Planck who first proposed this. And so I just said, what is a quantum? Here's your definition of a quantum. It's just the minimum amount of energy that can be lost or gained by an atom. And a lot of times we call them little photons. And if you've ever heard science fiction, the photon gun, and they're talking about is shooting out little bits of energy. So then this means we have an equation we can use here, and it's called Planck's equation. This is also on your reference sheet. So it just says that the energy is equal to H, which is just Planck's constant, times its frequency. And again, energy is in joules, frequency is in hertz. My note here, if you're looking through this through the book, they use a V, but they kind of do it like that as your frequency. Same thing. And then Planck's constant, again, it's a constant. It's on your reference sheet. This is something we always know. It's a given. So to do an example, we're just going to plug it in again. So what is the energy if I know my frequency, 6.32 times 10 to the 20th? What am I going to do? Use your equation. Well, I know Planck's. That's a given. What else do I know? Hertz. This is hertz. That is a frequency. I didn't put it, but I would put it down. What do I know? I know I have a frequency. So if I want to figure my energy, plug in Planck's constant is H, plug in my frequency. We're going to multiply it together. You're going to be needing to bring your calculator the next couple of days again, definitely. And you get your energy, and it's in joules. Okay, you have one more example. I want you to problem solve this one out using your reference chart, using what we've just looked at, and then we'll talk about this tomorrow in class. Okay. Long hair. If you have long hair tomorrow, bring something to tie it back. You need to be we're going to be dealing with flames in the flame test, and I don't want any long, loose hair flowing around. I have rubber bands if you forget, but I know that that's not the most comfortable. So long hair, bring something to tie it back. And try not to wear anything with really long, loose sleeves also. See you tomorrow.